Thank you very much, everybody, for coming. Um, so does anyone have any question about the last two lectures before we start? So everybody understand everything? Oh, that's great. That's unusual. Okay. So in the first lecture we talked about trend following, and in this and the next lecture we are going to talk about mean reversion trading. Okay. So this is to give you an overview of the space of trading strategies. By the way, I revised my PowerPoint slides and I add in the references. So even though you don't understand anything that I said or I'm going to say, it's okay. You can always go back to the references. So these basically are the papers that I take the materials from. If you download the lecture notes for lecture 1, I also put the references there. Okay. So let's start by talking about pairs trading. So the intuition is this: like there are lots of instruments in the market, and like for example, like NYSE alone has like thousands of stocks listed, and they cannot be all independent. In fact, they are highly correlated. The idea is that we try to identify two or more uh, assets that seems to move together. Okay. And the idea is like using the information from one asset or other assets, we're able to buy or sell the asset that we're interested in trading. Okay. Um, so the definition of pairs trading is usually you buy one asset and sell the other one, but it doesn't have to be true. Okay. I mean, basket trading is a generalized concept of pairs trading. So essentially, you will be buying a few assets and then you are selling a few others. So basically, you buy one basket and you sell the other basket, and the composition of the basket can changes over time. Okay. The idea is that you try to make money from the spread, and we're going to define what a spread means. Okay. So let's give you an example of the intuitions and see whether it makes sense. Okay. Well, again, the idea behind pair trading or basket trading is that market instruments they are not independent. They move together in some way. So here's an example. Okay, for example, let's say the Fed decide to cut rate. Okay, because as everybody knows, interest rate instrument or fixed income instrument is about interest rate. So whenever there's an interest rate change, the bonds or the fixed income instruments, they just jump. Okay, they just react to the rate immediately. Okay, and currency exchange is also about interest rate, right? Um, it's about the interest rate of the local currencies versus the foreign currencies. Okay, so FX also react. Okay, and then like when after the bond react, after FX react, then the stock may react, right? Because the people may shift the money from bond to stock or shift the money from FX to bonds, like that, and then everything else in the market react. Now I say it like I said as if there's a steps for the instrument to react in sequence, but in reality they all react more or less at the same time. Okay, I'm just using a very simplified example to illustrate that when something happens in the market, the whole market move, especially for interest rate. Interest rate is probably the uh, single most important indicators, or interest rate is probably the single most important piece of information in the entire market. It determines everything. Okay, so when interest rate change, everything change. But the key point is that like they don't all react at the same time. Like in the real world, even though like you know that after interest rate moves, everything will react, but that everything like they don't all react at the same time, because like that some react faster, some react later, and some don't even react. For example, okay. So you see like is that creates the arbitrage opportunities. So I give you some so I capture some pictures of the price movements of gold versus silver. So this is the 10 years prices of gold versus silver. You see commodities, right? They're commodities. They move more or less in the same manner. So when gold goes up, silver goes up, and vice versa. So this is the picture for the last 3 months. You see that they move more or less in the same manner. Okay, and this is the prices in the last month. You see that like over different horizons, gold and silver, they seems to follow one common trend. Okay, but as a mathematician, of course, we need to define what a trend is. But as we're gonna do that later. Okay, so the idea is again like instruments, market instruments, they are not independent. They are related to each other in a very complicated way. They're correlated, they move together, and they react to the news together. Except that they may react not simultaneously, but they may react, some react faster, some react slower, and that forms the basics for pairs trading or basket trading. Now, in order to do pairs trading, there are two important questions that we need to ask or answer. So the first question is like, how exactly do we construct a pair? Okay, and the second question is, after we have the pair, how do we trade them? Okay, this lecture 2 is this second theoretical class is going to focus on how we construct a pair. Okay, and then the next theory class we're going to talk about how we're going to trade a pair. Now, the pair construction is a very big topic. Okay, there are many academic research that talks about this. Okay, we are only going to touch the very surface of it. Okay, we're going to only touch the very basic materials. Okay, and in the full CQI course, we're going to talk about the details of the advanced method to construct a pair. Okay. Okay. Let's start with a very simple pairs trading strategy as a sample. Okay, this could be like simple sample. Okay, so this is a simple sample of pairs trading strategies. Okay, but it illustrates the concepts involved. For example, we're going to define spread as a linear combination of the assets involved, and the simplest thing is like x minus beta y, and beta is the hedge ratio. And the idea is very simple. Like basically, from the underlying asset or from the lateral asset that exists laterally in the market, you create a synthetic asset out of them. Okay. So in this case, Z is a synthetic asset, and that is created out of X and Y, and X and Y are the lateral assets that exist in the market. Okay. And when you are trading this synthetic asset, you are essentially trading both X and Y. So for example, when you buy Z, let's say when you buy 1 unit of Z, you're buying 1 unit of X, and you're selling beta units of Y. Okay, and likewise, if you're selling Z, you are selling 1 unit of X and buying beta units of Y. And in fact, after we do this basket construction, meaning that like we fix beta. So basket construction in this case is very simple. It just means how we choose beta. Okay. So after you choose beta, then your basket is fixed. Your basket construction is done. It's just a matter of how we trade this. Okay. Now in this case, we can treat Z, the synthetic asset, as any other asset. So we can analyze the time series behaviors of Z, just like we analyze the time series for X and Y. Okay. So that's how we trade it. The idea here is the linear combination. Okay, like the key point here is the linear combination, because that's something that we can buy or sell. Like if you say Z equal to XY, like and then we don't know how much X to buy and how much Y to buy, right? So linear combination is very important. Okay. Now this is the spread that most people use. It's based on the price. Okay, so X and Y are the prices. But as we mentioned in lecture one, often we don't we don't analyze the price data. We analyze the return data, and specifically we analyze the log return data. Okay, so so log X is basically the log prices, and if you have log X1 minus log X2, then you have the log returns of X. Okay, so this is the log spread. The idea is it's the same. You buy certain units of X and then you sell certain units of Y. Now then the question here becomes like how like for this log spread, it's not clear that how many units of X we buy or sell, or how many units of Y we buy or sell. Does anyone have any ideas like how for log spread, how do we determine the quantities of X and Y? Let's say we want to buy 1 unit of Z. What does that mean? Anybody know how to approach this problem mathematically? How do we even start it? Anybody know? Hector, you have an idea? How we can how we chase Z? Let's say we want to buy 1 unit of Z. What does that mean? No, you need to be more. You need to be more specific on this. Like, it's not obvious to me what exponential means to me in this case. Or can or how? Do you guys have any idea what it means by trading Z in this case? This is a linear combination of X and Y, except that it's linear in terms of the log price. No, not quite. We can actually try to do a little bit of mathematics. Yeah, but what exactly is by 1 unit of log X? Of course, but what's log X? X is like say Microsoft. So what is the 1 unit of the log of Microsoft? It's not obviously what that means. Okay. So let's do a little bit of math and see if you can follow. Okay. So I'm gonna switch my screen to So I'm gonna share my view. Okay. So can everyone see my screen? I'm sorry. I want PowerPoint. So everybody see my screen? Okay, good. So let's do a little bit of math. Like here's how you analyze the problem. Okay, here's how you analyze the problem. So first of all, let's understand what it means by buying and selling Z. Okay, so what does it mean by buying 1 unit of Z? So it means like when Z goes up, you make some money, right? But how much money do we make here? So here's what we do. Okay. So this is the definition of Z. So log X minus log Y. Let's say beta is 1 in this case. Let's say beta is 1, okay, just to keep it simple. Okay, so in this case, let's say the price of Z goes from Z1 to Z2. Okay, so this is Z1. Okay, and this is so it defined like this, right? This is our definition. Everybody see that? Everybody follow? Okay, so again, and then we have Z2, same thing, right? Except that we change the subscript. So how you love it to do math in Excel, in PowerPoint, huh? Okay, so what's the return? So how much money do you make when the price go from Z1 to Z2 if you're holding 1 unit of Z? So here that it's just this, right? It's just Z2 minus Z1, right? Now, by the way, like the reason why I wanted to show you the mathematics is like I asked you this question, and all of you guys just give me a random answer without thinking about it. Okay, so this is not the mentality to do quantitative trading. In quantitative trading, you need to justify all your answers by mathematics. Okay, so so the idea is that you need to get in the habit of like thinking in terms of mathematics, thinking whether your answer can be justified. You don't just like throw a random answer, say like, oh, okay, exponential or ratio divide by z or something like that. No, I mean, these are not like, this is not the mentality of a mathematician. Okay, so you need to get into the habit of thinking in details in terms of mathematics, and that's why I'm drawing this for you, just to show an example of how to do it. Okay, so show you exactly the variation. So basically, this is what we have, right? If this is the amount of money that we make, if we buy 1 unit of Z and the price go from Z1 to Z2. So what exactly is this? So let's do some derivation now. So this is really depend on how good your mathematics is. Okay. Okay. So what is this? This would be just like log x2 minus log x1, right? And it would be what's log x2 minus log x1? It's just this, right? This would be just like x2, and this would be x1, and you have it minus the same thing, except this is log. Okay, so why is this helping us? Like, what is this telling us? So what's the next step? Anybody can guess what the next step would be? So we have the log return. Okay, so we have the log return. So what is it? What's the next step? Anybody can guess? The idea is like when I'm doing the mathematics, hopefully you don't just like watch. You should be thinking what the next step is, so you can like challenge yourself a little bit in the head by doing a little bit of mathematics. Okay, so it's not obvious what the next step is, right? But let's leave it like this for now. Okay, let's leave it like this. So we put it here, put it aside. We'll put it here first because we have no idea where this go. Okay. But this still does not answer the question of how many unit of x or how many unit of y we're gonna buy and sell, right? So we need to do more mathematics. Let's try this. Let's say I want to buy let me tell you the answer. The answer is that you buy equal dollar value of x and y. So what that means is like if you have like $1, you buy $1 worth of x, and then you sell $1 worth of y. Now in the general case, you buy when you buy 1 unit of z, what that means is that you buy $1 worth of x, and then you sell beta dollar worth of y. So let's try to see whether this works or not. Okay. So in this case, our beta is 1. So it means what? We buy $1 worth of x, and then we sell $1 worth of y. So so how many unit is $1 worth of x? Anybody can guess? It's very simple, right? $1 worth of x is like you have $1 and you want to buy and the price of x is x. Okay, so you buy this is the $1. This is the number of unit of x that is worth $1, right? Everybody see that? Okay. And so when the price go from x1 to x2, how much money do you make? When the price go from x1 to x2, how much money do you make? You make exactly this, right? You make x2 minus x1. Okay, so this is how much money that you make if you buy $1 worth of x. Okay, so likewise, you do the same for y. You do the same for y. Okay, so you do the same for y. So 1 over 1y is the is the amount, is the $1 worth of Y at time 1. Okay, so this is how many unit of Y you buy. So this is the amount of money that you make. Now if you put them together, so basically you're buying 1 unit of X. I'm sorry, you're buying $1 worth of X, and let's say you want to sell $1 worth of Y. So here's what you have. That's what you got. Okay, we don't need that. So what is this? Does this look familiar now? So let's do some algebra. Okay, so it's just basically so x2 over x1 so it's just the x2 over x1, right, minus y2 over y1, right, y2 over y1. Now this is minus 1, right? X1 divided by x1 is 1, and then y1 divided by y1 is 1. So this is minus 1 plus 1, so the 1 get cancelled. Now if you compare this equation to this equation, they're exactly the same, well, more or less the same. Why? Because this is the log return, this is the I don't know, the ratio return or something. Now if you remember in your high school algebra class, you know that log x is more or less the same as log r is the same as r, right? When r is very small. So you see these two equations are exactly the same, right? So it shows that, it shows what? If you buy and sell xy using this ratio, say 1 over x1 and or beta over y1, then the return when the price goes from z1 to z2, the return would be the same. Okay, so it basically means like when you want to trade, when you trade the log spread, the amount of x to buy and the amount of y to buy is determined by the dollar value of the asset. So in the general case, let's go back to our, in the general case, so in the general case here, the log spread, it means what? We buy when we buy 1 unit of Z, we are essentially buying $1 worth of X and selling beta dollar worth of Y. Okay, and likewise, when we are selling Z, we are selling $1 worth of X and we are buying beta dollar worth of Y. Okay, so this is how we trade the log spread. And as we shall see in the next theory class, we're going to use the log spread instead of the regular spread that everybody uses. Okay. So how do we determine beta, by the way? So again, once we choose the form of the basket, let's say a linear combination of two assets, then the basket construction problem just becomes how we choose beta. Okay. There are many ways to do it. One way to do it is just by random beta, such as setting beta to 1. Okay, so x minus y. But there are other clever ways to do it. For example, if you have no money, okay, you have 0 money, then you can consider using this dollar neutral hedge. The idea is like you buy you try to sell something to get some cash, and then you use the cash to buy another thing. Okay, so for example, in this case, suppose we have the S&P 500 E-mini future, and it's valued at 12.20. Okay, and each one is $50. So the dollar value is 61K. Okay, and suppose we also have the last step futures, and the dollar value is 32, and then we just figure out the dollar ratio. Okay, this is the dollar ratio. It turned out to be 1.87. It turned out to be 1.87. So the idea is like if we first sell say 1.87 contract, like of course we can't sell 1.87 contract. So but we can round it to the nearest integer. So let's say we sell 19 contract of NQ, and we get a cash, and then we can use it to buy $10. I'm sorry, you can use it to buy 10 years contract, which is worth exactly the same amount of money. Okay, so you can construct this basket out of thin air. Okay, you pay nothing, but you enter into a position. Okay, and this is the dollar neutral hedge. So the idea is that you choose beta so that you don't have to pay any cash upfront to enter the position. Okay. Another popular hedge is the market neutral hedge. So let's say so the idea is that you compute the market beta of the two instruments. The market beta is like the thing that you learn in investment 101. It's the sensitivity of the instrument to the market. Okay, it's computed using some sort of OLS, the ordinary least square. Okay, so the idea is construct a portfolio so that the market beta of the entire portfolio is 0. Okay, in that case, your market, your portfolio should not be affected by the market movement, theoretically. Okay. So these are the popular ways of choosing beta. But are they good? Probably not. The idea is like there's no reason why the beta chosen this way will make money. Okay, and in fact, this beta changes all the time. For example, the price for ES and NQ for these two futures, they changes every day or every second. So the beta will changes every second, and the market beta changes all the time. So beta changes all the time. Okay. And you need to recalibrate from time to time. But the idea is like, I mean, these beta are just chosen in a convenient way. Okay. So for example, first where you pay nothing out of the pocket, and second where you try to make it market neutral. But there's no reason why a basket construct this way will make money. Okay. There's no reason for that. But let's say we use one of these method to choose beta. So now we have a basket. But we can do this for many pairs in the market, right? Let's say we have 1,000 instruments. So we can we how many pairs do we have? We have almost 1,000,000 pairs, right? 1,000 multiplied by 1,000 is 1,000,000. So okay, you have 1,000,000 pairs. So out of these million pairs, which one do we choose? Okay, which one do we choose? One way to do it is like we can consider distance of the pair, meaning that we consider the distance between two time series, and then we choose the one that has the smallest distance. Okay, so the idea is that the smaller distance d is, the more closely related these two time series are. Okay, so that's just intuition behind it. But again, because in pairs trading, the motivation is that we choose two assets or basket of assets that are closely related to each other. They move together. So the distance between two time series is a good way to measure how closely related they are. The idea is that the more closely related they are, the smaller the distance. Okay. But here in this case, you have to notice that the prices x, y, are the prices, but they are not the regular prices. They are the normalized prices. The idea is this. Let's say you have what's the dollar value of Apple now? Is that trading around 450, 480? The idea is that let's say you want to trade a pair, Apple, okay, minus. Anybody know a penny stock? Okay, a penny stock. Okay, now if you just use the raw prices, then this thing makes no sense because it will be just like say 500 minus 0.001. It is more or less the same as 500. So if you just use the raw price, then the distance is always dominated by the big guy, okay, by Apple in this case. So the value is almost more or less around 500. Okay, so in order to avoid this scaling problem, we use the normalized price. Like normalization usually means the number of standard deviations. Okay, so a normalized price would be like this. Normalized price equal the number of standard deviation from the mean. Okay, so it would be like x small I would equal to the price of x and I minus the mean of price divided by standard deviation. Okay, so this is a normalized price. The idea is that you remove the scale from the prices, so you can compare two prices that are very different. Okay, so in this case, it may just say, so in this case, we could just have say, for example, apple would be equal to 0.5 standard deviation minus 0.35 standard deviation. Now this number looks more or less similar now. Okay, so we can compare them. So the idea is that when we this happens very often in pair trading. When we compare prices, we most of the time we use normalized price. Okay, to take away the scale. Another way to do it is we can use the log of prices, like as in log spread. Okay, here. So we can use the log of the prices, and to some extent we move the scale as well. Okay, right. Okay. So the strategy. So here we construct like we talk about how we construct a pair by choosing beta. Okay, and then among all the pairs possible, we choose the closely related one. Okay, and then the next question is that how do we check? Like one very simple thing is like when Z goes up you sell. Okay, when Z goes down you buy. So when, for example, when Z is above 2 standard deviation from the long-term mean, you sell. When Z is below 2 standard deviation, you buy. Okay, so this is more like Bollinger Band or the other technical indicators. Okay, the idea is like will they work? Nobody knows. How good they are? That question we can answer. We can know how good they are, but we're going to talk about it in the next lecture. Okay. But you see the idea. The idea is like after you construct a pair, when the price of the synthetic asset goes up, you sell. When the price goes down, you buy. So buy low, sell high, right? So that's the basic ideas. Okay. So here I talk about when Z goes above 2 standard deviation, we sell. When Z is below 2 standard deviation, we buy. The idea is that when we talk about the price of the synthetic asset, in order to evaluate whether this is expensive or cheap, we again do a normalization of the Z price. It's called a Z score, just a fancy name for the number of standard deviation from the mean. Okay, you see this is exactly what I got here. Okay, so the current price minus the mean divided by the standard deviation. Now, in order to actually carry out this formula, you somehow need to know the mean and the standard deviation, right? But of course, you do not know. I mean, you do not know the future mean and the future standard deviation. What most people do is like they keep track of a rolling window. Okay, so let's say a rolling window of 60 days, and then they use the data in that 60 days to compute the mean and the variance or the standard deviation. Okay. But you can add a lot of fancy stuff to these basic ideas and make it proprietary. For example, in one of the paper that I wrote, they actually use this particular form. M and S are numbers, they're scales, but they're functions. Okay. Basically, they're saying by using this skill form of the Z-score, they can do better forecasting. I don't know whether this is true or not. I personally have not tried. But I'm just telling you like this is what the paper claims, and some people do modify the basic ideas to make it somewhat proprietary, and hopefully for better forecasting power. Okay. So here I said it already. So when Z becomes expensive, meaning that like it's 2 standard deviation above the long-term mean, you sell. Based on our pair, when we are selling Z. What does that mean? Is when we are selling Z, we are selling 10 contracts of ES, and then we are buying 19 contracts of NQ. Okay. So this is a very simple trading strategy based on a distance. Okay. What are the advantage of the distance method? First of all, there's no model. Okay, like based on everything that we just discussed, there's no model. Okay, and the advantage of no model is that like you will not have any misspecification problem because there's nothing to specify. Okay, and there's no misestimation problem because there's nothing to estimate. When you have no model, you have nothing to specify and you have no parameters to calibrate. Okay. The idea of the distance method is that it captures the law of one price, because the idea is that like when two assets are very closely when they are very close to each other and they move together, they are essentially behave as if they are one asset, so they should have one price. Okay, and that's why when one goes up, the other is supposed to go up, and one goes down, the other is supposed to go down. Okay, the law of one price. Okay, so what are the disadvantage of the distance method? The disadvantage of the distance method is exactly the same as the advantage of the distance method. That is, there's no model. Okay, when there's no model, then there's no assumption. There's no assumption. You can't analyze it. There's no reason why the strategy will work or will not work. Okay. When there's no model, there's nothing to analyze. You cannot say, remember in lecture one, we say like in quantitative trading, we want to ask question like what's your expected P&L, what's your expected holding time, and also of like questions like this. But here, because there's no model, you can't answer any of these questions. Okay, there's nothing for you to analyze when there's no model. Okay. The advantage of the distance method being model free is also the disadvantage of the distance method. Okay. There are more problems to use this method. The idea is that it basically ignores the spread as a process, and it treats that the price of the synthetic asset or the price of the spread just coming up from a random number generator. All the z's you see are IID. So basically, Z1 today, Z2 tomorrow, C3 blah blah blah. They are essentially IID. Meaning that independently and identically distributed random variables. And it's not a process. It's just like it treats the spread as a random number generator. As we shall see, if this is true, then of course this is very good. But we wouldn't expect this to be true, right? We expected that the spread of the pair or the price of synthetic asset follows some sort of like stochastic process. Okay, so the distance method is making a very unrealistic assumption on how the spread works. Okay. Another problem of using the distance method is the way that it filters out pairs. Like, remember how we filter out pairs? Basically, we compute the distance among a million pairs, and then we choose the one that has small d. Now, if you really do have a million pairs to choose from, then of course you can throw away a lot of them. Okay, but it may only work for equities. Like say in FX trading, like let's say you're trading G7 currencies, then how many pairs do you have? You have what? 79 minus 7 pairs, right? So 72 pairs, right? 7 times 7 and then minus 7. So 72 pairs. If none of them works, then what do? You throw away all of them, and what do? You have no pairs trading. Okay. So so the distance method it has many problems. The reason why I show it to you is that I want to use this method to illustrate the concepts of pairs trading. Okay. So what are the risks in pairs trading? Oh, by the way, what's the biggest risk in trading? What's the biggest risk in trading? Everyone knows. I mean, you as a trader, okay, what's the biggest risk in trading? Right. Maybe this is too sophisticated. Okay, so the biggest risk in trading is losing money. Okay, of course. This is very deep, okay? Philosophically. So what contributes to losing money? Okay, in pairs trading, obviously one thing that you will lose money is that the long-term equilibrium does not hold. Because the pairs trading is about long-term equilibrium. Okay, like when you buy Z or sell C, it just means that there's a disequilibrium. Okay, it's a deviation from the long-term mean. When it goes up, okay, you sell because it deviates from the long-term mean, and likewise when it goes down, it's also a deviation from the long-term mean. Okay, so the worst scenario that could happen is like, let's say you buy A and sell B. When you buy A and then the company goes bankrupt, okay, and then B does not move, then you lose a lot of money in your pairs trading, right? And likewise, when you buy A and sell B, and then B skyrocket, okay, you shock B, but then B price keep going up, and A goes bankrupt, then that's the worst thing that could happen, okay? But that does actually happen, right? Let's say you have the two companies A and B, and they are both in the same industry. Let's say they both produce operating systems, okay? So but A ultimately wins over B, okay? So A becomes the dominating player in the market, and B goes bankrupt, okay? So only A is selling OS now. Of course, A goes up, B goes to bankrupt. Now, but if you're constructing a pair that if you long B and sell A, then you will go bankrupt as well. Okay, so that's a risk in pairs trading. And then also it's subject to the other regular risk, as in any other trading strategies, like the systematic risk and the firm specific risk. The firm specific risk is like things like say the CEO dies. Okay, so like Steve Jobs. After it dies, Apple goes down and down and down. Okay, that's the firm specific risk. Okay, and it affects the long-term equilibriums of any pairs trading that involve, say, Apple in this case. Okay, liquidity problem is very specific to pairs trading. The idea is that when you are trading X and Y, what it means is that you need to buy X and sell Y at exactly the same time. Okay, at least at exactly the price that your model tells you to buy and sell. If the just because you want to buy something doesn't mean that you will buy it, right? It also depends on bid ask and all that stuff, and whether there are enough liquidity that you can buy. So liquidity could be a problem if you're trading not so liquid stock, because when you want to buy, you can't buy, and when you want to sell, you can't sell. Or even worse, I mean, there's no short selling allowed for the instrument that you want to go short. So there are these like practical constraints that you as a trader need to consider when it comes to pairs trading. Okay. So as a small summary, what pairs trading involve is like number one, the pairs construction. Okay. Number two, how we trade it. Okay. For simple linear combination of stocks like z equal to x minus beta y, basket construction is just about how we choose beta. Okay, let's go back here. So here in this case, basket construction is just about how we choose beta. We mentioned two simple ways to choose beta, but there's no reason why this will work or will not work. Okay, so we want to analyze the problem of choosing beta from a mathematical perspective. Okay, and that will get us to co-integration. Now, co-integration is probably one of the most popular methods in pairs trading. Okay, but this is not to say that it works. Okay, it's not to say that it works. It's just saying it's a very popular way to do it. So co-integration in fact tells us how to choose beta. Okay, but let's start with the basic concept. Stationarity. Now, stationarity is probably one of the most important statistical properties in trading. Stationarity means what? It means something doesn't change. If that thing doesn't change, then you can make prediction about it. Okay, you can make prediction about it in the future because you expected something. You expected the property that is today that you can observe remains the same in the future. So you can make a bet based on this confidence. Okay. What stationarity in statistics means? Well, what the question was, what is stationarity in statistics means? Well, obviously it means the statistical properties of something does not change, right? So how do we describe a statistical properties? Usually we describe by probability distribution. So it means stationarity means that the probability distribution of the random variables or the random time series does not change over time. Now, probability distribution of random variable does not change over time is very easy to see. For example, if I have a normal variable like this, when I say it's stationary, when I say x is stationary, it just means that today is normally distributed, and tomorrow it will be normally distributed. Okay, and the day after it will also be normally distributed. That's what I mean for for random variables. But what does it mean by a stationary time series? Okay, that's not so obvious. Okay, the strong stationarity means that the probability distribution of the joint probability distribution of any finite number of xt, for example p, x1, x2, x3, does not change over time. Okay, so the joint probability of these three observations does not change over time, but it needs to apply for any finite combination of the observations. So you can have like x4, x8, x9, x10. So that's basically what I'm saying. So this is the strong stationarity. Okay, so it's basically the joint distribution of any finite number of observations do not change over time. This is strong stationarity. But this definition is very difficult to use. It's not practical, right? Because it's very difficult to check for all the possible combination of observations, let alone the joint distributions of them. Okay. So we usually don't use this definition because it's too complicated. It's only of theoretical interest. Okay. So what we usually care is what we call the weak stationarity. So we only care about the first and the second moments. So as long as the first moment, the mean, does not change over time, constant, and the covariance xt and xt minus L does not change over time, then we are happy. L is the fixed number, is the number of legs. Okay, so this is the weak stationarity. It's also called the covariance stationarity. So basically it's saying the expectation does not change over time. So that means that there's a long-term mean. Okay, so that implies that there's a long-term mean because the expectation is the long-term mean. Okay, and then the covariance does not change over time. So basically saying the covariance of today's value and tomorrow's value does not change over time, and that provides the basis for making prediction in the future. Okay, and likewise, when the covariance is constant, another implication is that the variance is also constant, right? Because the variance is just the covariance with itself. Okay. So you see that both the first moment of the time series and the second moment of the time series does not change over time, and that provides the basis for us to making any prediction. Okay. So that's stationarity. So basically, so you see that like if we do find some asset or synthetic asset that is stationary, that means we can make a lot of money. Because stationarity implies mean reverting. Why is that the case? Here, that's the reason. Stationarity means that there's a long-term mean. Okay, what that means is that whenever the price go up, we expect it to go down back to the long-term mean, and whenever the price go down, we expect that it will go back up to the long-term mean. So this stationarity implies a mean reverting process. Okay, when we find a mean reverting process, and we know that if it continues into the future, then we know that we found a gold mine. Okay, again, you can buy low and sell high. So any deviation from the long-term equilibrium, any deviation from the expectation, signals a trading opportunities. Okay. Now this start to deviate from technical analysis. Okay, in technical analysis, you just say, oh, when it goes down, you buy. When it goes up, you sell. For any mean reverting asset. But in technical analysis, mean reverting asset is never a well-defined concept. Okay, It just says something moves like a wave, then it's mean reverting. So here's what I'm saying. So in technical analysis, when you say mean reversion, it just means this. So the price will go like this. So that looks like mean reversion, okay? But looking like this is not a mathematical definition. Of course, like something look like this is mean reverting, but what exactly is looking like this means? And how exactly do you quantify a process like this? Or another question that you want to ask is like, how mean reverting is a process like this? Okay, can we put a number? Can we put a number to tell how mean reverting a process is? Okay. In technical analysis, there's no answer to any of these questions. You can quantify what a mean reverting process means, and you cannot tell how mean reverting a process is. But in quantitative trading, we can do that. Okay. In fact, so what we just described is a very strong form of mean reversion, stationarity. Okay. So stationarity is probably the strongest form of mean reverting. Okay. Stationarity implies mean reverting, but as we shall see in the second half of the lecture, even though something is not exactly stationary, we can still trade it as if it's a mean reverting asset. Okay, as we shall see. Okay. And in fact, we can answer the question saying how mean reverting an asset is. Okay, so in both quantitative trading and in technical analysis, we both buy low and sell high, and we both have the notion of mean reversion. But in quantitative analysis, we can quantify what exactly we mean by mean reversion. Okay, and then we can put a number in it. So how do we test whether something is mean reverting or not? Like given any time series, okay, given any time series, how exactly do we check whether it's mean reverting or not? Okay. There are many statistical tools that allow us to do this. Okay, if you go to the wiki page, for example, if you go to the wiki page, you go to wiki and you search for stationarity test, for example. Okay, Euler test. There you go. There are so I listed 3 of them here, but there are a lot more. It's not just these 3. These 3 are the popular ones, okay? But there are many Euler tests, or you can invent your own, okay? And the most popular one is this one, augmented Deficient test, okay? So the idea is that given any time like this, instead of just by eye browsing, instead of just based on a personal judgment, how exactly do we tell whether this is mean reverting or not? Now this looks like mean reverting, right? This one is obviously not mean reverting, it's just going up. What about this one? Sorry. What about this one? Is this one going up, or is it still mean reverting? Now that's not clear, right? So we can't just base it on our personal judgment. So what we want to do is that we want to have some sort of like theory that tells us, or put a number to tell us whether this is mean reverting or not. So one of the popular hypothesis testing way to do it is Dickey-Fuller test. The idea is very simple. The idea is this. The idea is this. Now, if a time series is stationary or mean reverting, then it means that if it goes up, we expect it to go back down, right? What that means in mathematics is that if we are seeing a very big value now, we expect the future value would be small. Meaning that like if we see a big value now, so if we see a big y now, we expect delta y would be negative, right? That's exactly what it means, right? If y is big, it means it's going up. Okay, it's now above the equilibrium, above the long-term equilibrium. Then we expect it to go down, and if we expect it to go down, then the changes in y, delta y, will be negative, right? And likewise, now if y is very small now, we expect it to go back up, then we expect delta y to be positive. Now, the idea is that if something is stationary or if something is mean reverting, then it changes in a time series. Delta y will be dependent on the current level y. Okay, so delta yt will depend on yt. Okay, so so here's the equation here. So delta yt will depend on yt if it's mean reverting. Otherwise, it will not. Okay. So the idea is that we assume this structural form of the time series, and we want to check whether delta yt depends on yt. And again, if delta yt does not depend on yt, namely that gamma equal to 0, then yt is non-stationary, right? Because again, as we just talked about, if delta yt, if the changes depend on the current level, then it's mean reverting. Otherwise, it's not mean reverting. And if it's not mean reverting, then it's non-stationary. Okay. So this all the method Fuller test is saying we assume this structural form for the time series involved, and we want to check whether delta yt depends on yt. And mathematically, it's equivalent to checking whether gamma is 0 or not. If gamma is 0, then it's non-stationary. Otherwise, it is stationary. Okay. And there's software to do it. Say Shenshu, our library, has this augmented Fuller test you can use to check whether a time series is stationary or not. Okay. Okay. So given any time series, we can check whether it's stationary or not using Euler testing, such as the ADF. Now the question is, how exactly do we choose beta in the first place, so that we have something to check? And the idea is co-integration. So co-integration is a way of selecting a linear combination of assets to construct a stationary portfolio. Okay, we can write this down more mathematically. So the idea is that given two assets x and y, okay, so given two prices xt and yt, we want to choose a beta, or co-integration will choose a beta such that it equals to this form. The long-term mean, mu is the long-term mean plus a stationary residuals. Okay, so basically you choose beta such that the linear combination, the symptotic asset set D, is stationary, and stationarity here is represented by a long-term mean plus a random noise. Okay, and by the way, we need to define something. We call this an I1 time series. Okay, a price is an I1 time series. But in order to define what I1 time series means, we need to define what I0 times. We need to define I0 time series first. Okay, and I0 is by I0 just means stationarity. Okay, I0 is defined as stationarity. Okay, or random noise, or white noise. Okay, like epsilon t, white noise. Okay, so by definition, I0 means stationarity because I0 is just white noise. Say IID white noise. Okay, IID white noise. I1 just means a summation of an I0 time series. Okay, so we can write this down mathematically. So I0 is just a random noise like epsilon t. Okay, that's I0. And I1 just means the summation of it. Okay, so say I1, say the price equal to summation of it. So I1 is the summation of I0 time series. Okay, now you see that the prices, like so, we say prices are I1 time series, meaning that the prices is usually represented just a summation of the random noise or a summation of the white noise. And a proper terminology for that is random walk. The reason why we say the price is a random walk is exactly because of this. It's the summation of the random noise. Okay. Now what's the what? So you can ask. This definition can go on and go on. So you can define an I2 time series. So what's an I2 time series? An I2 time series is just a summation of the I0. An I2 series is just a summation of the I1 time series. So we have this summation of YT. You can always write in terms of the white noise, the I0 time series. So it's just a double summation. Okay, so it's a summation of the summation of the white noise. Okay. So this is the I2 time series, as you can see here. It's a double summation, two summations. So it's I2. By the way, this I stands for what? What does this I stands for? Why is it called I stands for integration. I stands for integration. Same as in calculus. Yeah, Hector, you got it. Integration means summation. Okay, good. Okay, so basically, so the mathematical problem becomes well defined now. Based on this, you choose a beta such that you can write this equation in terms of this. Okay, so beta is now well defined. I'm sorry, the mathematical question is now well defined. The question is how exactly do we choose beta? Okay, and this is the subject of co-integration. By the way, before we get into the mathematics of choosing beta, we want to mention something about pairs jetting. Usually when we construct a pairs out of say stocks, we usually want to choose stocks from the same index Gs because they tend to move together. For example, I just show you the example gold versus silver. They're both commodities, okay, heavy metals. So they tend to move together, okay. Or you can choose, for example, Google versus Apple. They're both like technology stock, so they tend to move together because they subject to the same systematic risk, okay. They are subject to the same systematic risk. And therefore they are usually driven by the same fundamental factors. Maybe Apple versus Google is not a good example. Let's try Apple versus say Samsung. Okay, they both make phones. Okay, so when everybody is buying new phones, then both stocks should go up, right? So the same fundamental factor in this case would be the number of smartphone users, for example. Okay, so the consumer demand tends to drive these two stocks because they are in the same industries. Oh, by the way, co-integration. So as you can even see from this example, the goal of co-integration is to reduce the order of integration. So for example, the prices of x and y are of I1 time series, but after you choose a linear combination of them, then the linear combination become an I0 time series. So you reduce the order of integration by 1 in this case. It goes from I1 to I0. So you reduce the order of integration by 1. In general, what co-integration does is like it reduce a set of time series of order D by B. Okay, so the resulting time series, the linear combination, has an integrator for order D minus B. Okay, so D is the original orders of the underlying time series, and then co-integration reduce the order by B, and the resulting time series has an order of D minus B. Okay, and in general, beta is not unique. Now, in our example, we only care about what? In our example, we only care about this. In trading, most of the time we care about only CI 1 0, meaning that we start with prices that are of order 1, and then we reduce it to order 0. Like, why is order 0 so important? Again, order 0 means stationarity, and stationarity implies mean reverting. And mean reverting implies a long-term mean, and long-term mean implies an existence of a long-term mean implies this equilibrium is a trading signal. Okay, so we can type it. We write down the looks. Stationarity implies mean reversion. Okay, I0 is very important because it implies stationarity. Stationarity implies mean reversion, which in turn implies existence of a long-term mean, and it implies this equilibrium signals a trading opportunity. Okay. So this is what we talk about. So in this case, this should be C11, okay, because you reduced order by 1, okay. So in this case, you have D equal to 1 and B equal to 1. Okay, let's illustrate co-integration with a simple example. Like the mathematics inside the co-integration mechanics is very complicated. You have software to do it most of the time, so you don't need to really understand it. But in order to understand the intuition behind co-integration, we're going to illustrate it with a simple example. Okay. Now, Hector, you have a question? Well, the idea is that, like, usually assets from the same industries are usually highly correlated. Oh, that's a good question. So what are we trying to do here? What are we trying to do? We want to pick something that we want to pick a pair that has high correlation. Okay, but in order to do this, we usually pick it from the same industry, because same industry usually implies high correlation. Say we would expect, for example, Apple and Samsung has a higher correlation than Apple and really a firm that's selling apples. Okay, right? We will expect that because they're both technology stock. Another reason why we want to pick from the same industry is that it provides a reason. Like I said, because from the same industry, stocks from the same industries are driven by the same fundamentals. Okay, so there's no common factors between selling iPhone and selling apples, right? I mean, there's no correlation between iPhone and Apple, the fruit. For example, correlation is probably 0. Okay, but we will expect a high correlation between iPhone and asphalt, right? So that's why. So it provides an economic meaning. So basically, it provides an economic meaning to choose stocks. Okay, let's get back to the mathematics. Like I said, the mathematics in co-integration is quite involved. It's quite complicated. If you really want to challenge yourself, you can read Professor Johansen's book. Okay, this book is one of the most difficult book to read in time series, because it's written in such a very condensed manner. If you think that you're very good at time series, okay, think again after you read this book. Okay, so try to challenge yourself by reading Johansen's book. But the idea is that if you really want to be a good quant, then you should have the ability to read his book. Okay, because it really boosts up your time series skills. So in this book, it details the mechanics of doing co-integration, how to find beta in a very detailed manner. But again, the mathematics is very involved, so we are not going to reproduce it here. So what we want to do here is like we want to provide you with a simple example that motivates what's behind the co-integration mathematics. Okay, so we start with a simple var example. Var here stands for vector autoregressive. Okay, so it stands for vector autoregressive. Now, vector means what? Vector just means like multi-dimensional or multivariable. So it's a multivariable time series. We have two time series, y and z, so it's multivariables. So it's a vector. The vector is yt and zt. Okay. It's autoregressive means that it's a linear combination of the past legs. It's a linear combination of the past values, and you see that like yt, the current value, is determined by the linear combination of the last y value and the last z value. Okay, zt value. Okay, and likewise, the future zt is determined by the current yt and the current z and the last zt value. Okay, so vector is here and autoregressive part is here. Okay, so this is what we assume for the time series that we observe. Okay, so basically given the data of two time series, we assume that it takes this particular simple form. Okay. So how do we do that? So given the data, we assume this particular form. What's the next step? The next step is of course to estimate the parameters. So here we have four parameters to estimate: a11, a12, a21, a22. We estimate these parameters from data. There are many ways to do it. Like so, you can do OLS or you can do maximum likelihood or whatnot. Okay. So in other words, you have a statistical procedure and then you have software to estimate these parameters. This looks like a four parameter estimation problem, but in fact, it's a three. In fact, in practice, we always restrict one of the variables, and in this case, we restrict say a11 to take this form. Okay, so essentially we reduced a problem to estimate four parameters to a simpler problem of estimating three parameters, and there's a reason why we want to restrict one parameters, but the reasoning we do not go into the detail here. I refer you to the original references if you want to know why. Okay. So the estimation problem, we restrict one variables and then we run it through a software and then we can estimate this a11, a12, a22, a21. Now, Johansen's theory says that theorem 4.2 in Johansen's book says that in order for yt and zt to be co-integrated, then there are restrictions on the coefficients. Okay. Meaning that, for example, it needs to satisfy these two conditions. A22 needs to be bigger than mass 1, and then this thing needs to be smaller than 1. To summarize what we're doing here, let's write this down. So given the data set of two time series, we estimate a model for it. Okay. And then, in order for this model to be co-integrated, the coefficients need to satisfy certain conditions. Okay, so here are the conditions. Here are the two conditions. So let's see why these conditions are important. Okay, let's do some mathematics. So by the way, this is called a VAR form, a vector autoregressive form. We can write it in the vector error correction model form. Okay, so what it stands for is VCM stands for vector, meaning multivariate error correction model. And error correction means this is about the delta, the changes. So we have the delta the delta term here. Okay, so we write in terms of the changes. So here, instead of writing it in terms of y and z, we want to write in terms of delta y and delta z. And the way we do it is like we do some algebra basically. We given this equation, we subtract yt minus 1 on both sides here, and then we subtract zt minus 1 on both sides here. Okay. So you see, we subtract yt minus 1 here, and then we subtract yt minus 1 here, and then we subtract zt minus 1 here, and then subtract cd minus 1 here. Okay, and then so basically this is exactly the same as what we saw before. Okay, and then we can write in the matrix form. So this is basically delta y, and this is basically delta z. Okay, and then we write in terms of the matrix form here. So this equation exactly the same as this equation, and this equation is exactly the same as this equation. So these three expressions are all equivalent. Okay. Now, but with this VCM form, we can do some magic. Now, first of all, we look at this. So A11 is restrict to take this form, right? So we plug A11 here. So A11 minus 1. So you can do the algebra. So basically A11 minus 1 would equal to this form here, okay? And everything else remains the same. So basically we just replace A11 by its restriction here, okay? And we got this. So how do we get from here to here? Oh, that's where we go. So basically, if we treat this as alpha, okay, and then we can compute the beta. So basically, we can do something like this. Hold on 1 second. Okay. So I'm going to do some math here again. Okay, so the term, you see, and then supposedly beta is this. So this is alpha. And supposedly this is beta. So let's compute this. We need to compute alpha beta equal to what? Just equal to this, the product of these two terms, right? Okay, so you see the product of these two terms. So 1 minus A22, 1 minus A22, 1 minus A22. So that these two terms get cancelled out, right? 1 minus A22 and 1 minus A22. So they get cancelled out. And then A21, A21, they get cancelled out, right? So it equal to what? Equal just to minus A12. Okay, so alpha beta equal to minus A12. Now you see the magic here. You see the magic here. So you can this, so this term is alpha here. That's how we define this term is alpha. Now A12 is what? We just compare it. Is A12 is minus alpha times beta. Okay. So so this is alpha minus beta. So we can extract alpha, take out the term. We have like alpha y. So this alpha y minus alpha beta z. So this is minus alpha beta z. Okay. So if we take it out, you take out the common term alpha here, then the first equation here is just alpha multiplied by this plus the residual. Okay. And likewise, you can repeat the same math for delta c. You can also identify this common term here. Okay. You can also identify this common term here. Now, this looks like exactly what we really want because we can because we identify the beta. Okay, so if we choose beta as this term, so basically after we do the estimation, so we have the A11, A12, A21, A22, and then if we choose beta to take this particular value, okay, then we can identify a linear combination such that we can write both delta y and delta c in terms of this linear combination. And namely, this linear combination is the long-term equilibrium, is the common trend to both y and z. You see that? So this is magic, right? So the idea is like, given a data set, you do the estimation, figuring out what those A11, A12, AZ1, A22 are, and you write if the coefficients satisfy these conditions, then you can write the VAR form in terms of the VECM form, and with the VECM form, you can identify the common trend, and the common trend is defined only by the beta. Okay, so you see this is the magic behind co-integration. It's basically saying when the coefficients satisfy certain parameters, then you can identify the common trend by picking the right beta, and the beta in this case is just 1 minus A22 divided by A21. There's more to this equation that you can try to interpret it for. For example, y minus beta z is the long-term trend, but what's the alpha term? The alpha term is like gravity. Okay, so this is the long-term trend. This is this line here is the long-term trend. This is the y minus beta z. This is y minus beta z. Okay, the long-term trend. Alpha is like gravity. The idea is like, you see that like let's say alpha y is negative. So basically when this term is very big and alpha y is negative, so when this term is very big, okay, so it means what? It means like, let's say this term is very positive. It means what? It means y is a lot bigger than z. It means y is a lot bigger than z, right? Zt in this case, because when this is big, then y is big and z is small. And since alpha y is negative, so it means that delta y would be negative, right? So when y is very big, delta y will be negative, meaning that you pull down y. Okay, so here you go. So when it deviates from the long-term equilibrium, then the alpha term will pull it back to the equilibrium. So the alpha term here is like gravity. The stronger it is, the bigger the pulling force, the statistical pulling force that pulls the time series back from the disequilibrium to the long-term means. Okay, so remember, like we just mentioned that in technical analysis, we cannot define what in technical analysis they do not define what mean reverting means, and they cannot tell you how mean reverting the assets are. So in quantitative trading, we can define exactly what mean reverting means by defining stationarity, namely whether beta exists or not. Okay, if beta exists, then we can quantify how mean reverting this thing is, or how strong the statistical pulling force is. They are measured by alpha. Okay, so again, alpha is like gravity. The bigger it is, the bigger the pulling force that pull the time series back to the equilibrium. and the equilibrium is just like this term here. This term is actually, you can consider as this equilibrium as well, because this term is the long term equilibrium, but it actually measured this equilibrium. Okay, the bigger this term is, the more deviate the time, the more the time series deviates from the equilibrium. Okay, so beta. So again, let's have some summary. Beta defines the co-integrating relationship. It defines the stationarity of the long-term equilibrium, and alpha measures how big the pulling force is. Okay, to pull the equilibrium back to the long-term mean. Okay. So basically, it's saying, so this is just a theoretical result. It says if x is co-integrated, then the VCM form exists. Basically, it's saying if the time series is co-integrated, then these coefficients conditions are satisfied, and then you can write it in the VCM form. Then the VCM form exists. Okay. Just a theoretical result. And when the VCM form exists, you can write the changes in terms of the disequilibriums and the lag increments. Okay, so this is the disequilibrium, the level. This is the level, is the disequilibriums. But then you can write the changes in terms of the past changes. Or in other words, you can write the increments in terms of the past increments. Okay, so in our example, this is what we got, right, in our example. So basically, this equation here, this vector equation is exactly the same as this equation here, except that I replace this by alpha, this returned by minus alpha beta. So alpha minus alpha beta. Okay, so this equation is exactly the same as this equation here. Okay. So gradual causality, what does that mean? It's like if a variable enters into the equation of an entire variable, then there's a causality relationship about it. This is very easy to see, right? Because let's just look at this equation. This is very easy to see. It's basically saying, like, because like yt is determined by the current value of yt and also the current value of zt. So it's basically saying there's a gradual causality relationship between yt and zt, because the past value of zt will affect the future value of yt. Okay, so this is a mathematical way to define what causality means among the time series. So basically, one factor that determines y, or one thing that causes y to happen is zt, and likewise, one thing that causes zt to happen is yt. Okay, so there's a causality relationship between the time series, and they can be well defined just by the structural equations of the time series. Okay. So this example shows that beta can exist. Okay, beta can exist for a multiple time series. But in general, we cannot just do this. In general, you cannot use this procedure to compute beta, right? Because what we just show you is just an example for a very simple, actually the simplest VAR model. In general, you can have like many lags here, and they can get a lot very complicated. So in general, we need a general methodology to compute beta. There are two methods to do it. Historically, Angle and Granger proposed the first method to compute beta as basically by doing linear regression. Okay, so you first regress yt against zt, and then you regress zt against yt to compute the betas. And once you compute the beta, once you do the linear regression, you can compute the residuals, and then you check whether the residuals themselves are stationary. If they're stationary, then you found the beta already, right? Just by definition. And the way you check whether zt, and then the way that you check whether the residuals are stationary or not is typically done by the ADF. So we just talked about the ADF, right? The augmented decay Fuller test. So this approach, the advantage of this approach is that it's very simple. Okay, all you have to do is to run some linear regression and do some hypothesis testings. Okay, but the disadvantage of that is that it only works on 2 time series. Okay, now this doesn't work when there are like 3 time series. Okay, so if you trade, if you're doing pair trading, pair by definition means 2, then okay, you can use this. But if you want to trade a basket of 3 assets, then this doesn't help. Okay, it doesn't work. And more importantly, this is the 2-step procedures, so it's subject to a bigger estimation errors. Okay, I think most people don't use this. Most people don't use this. And then the other approach is it's called the Johansen Procedure, and this is what we're going to talk about. Okay, this is what we're going to talk about. The Johansen Procedure, well, it's invented by Professor Johansen, obviously. He got credit for it. But the whole theory is just based on one very important observation. Okay, the whole Johansen theory on co-integration is based on one very important observation. It's this. Now, after you write down the VECM form for the time series that you want to study, then you want to study the coefficient matrix. Okay, so this is the coefficient matrices for the time series we had. We call it pi matrices. Okay, this equation I just copy and paste it from here. It's the same equation here, and it's the same equation here. Okay, it's from our estimation, and this is called a pi matrices. And the Johansen theory is based on one very important observation. It's saying if the time series are co-integrated, then the pi matrices, then the rows in the pi, then the columns in the pi matrices are not linearly independent, meaning that this is not a full rank matrices. Okay, everybody understand this? Or am I making sense here? Or am I talking to myself? So this is very important. You need to understand this. So let's look at this particular example. Let's look at these 2 rows. Okay, so the pi matrix is not a full rank matrix, meaning that like the rows or the columns are not linearly independent. So we can check that this row is not linearly independent from this row. So the way you check it is like so this is row 1 here, right? This is row number 1, and this is row number 2, and they are related by vectors. So if you multiply this vector by this vector, then you get this vectors. So it's basically saying this matrices here, this pi matrices, this coefficient matrices, is of rank 1. Okay, but since this is a 2 by 2 matrices, a full rank 2 by 2 matrices has a rank of 2. Now, since it has a rank of 1, meaning that 1 linear independent vectors, this is not a full rank matrix. And since this is not a full rank matrices, this time series is co-integrated. As we just saw, we proved that this time series is not co-integrated. Okay. Let's skip this. So in general, we can have this conclusion. Now, so this is all the Johansen theories based on this particular observation. After you do the estimation, you examine the pi matrices. Okay. Now, if this is already a full rank matrices, then the time series themselves are already stationary. Okay, they are already stationary. You do not need co-integration for them. Okay, because they are already of I0. Okay. Now, if the rank of the matrix is 0, that means there's no co-integration relationship possible among the time series. Okay, so these 2 cases are not very interesting. The interesting cases is when it's a deficient rank matrices, meaning that it's not a full rank matrices. Then in this case, you can decompose pi into alpha and beta, and co-integration relationship exists. Okay. this is very interesting because the pi matrix really tells everything about the co-integrating relationship. The rank of the pi tells you whether co-integrating relationship exists or not, and moreover, it tells you what the beta is, okay, and it tells you what the alpha is. Using our example here, so this is the pi matrices. You see that it can be decomposed into the product of alpha and beta. You see that? So, and see, this is the pi matrices here. So you see that pi matrices, they can be decomposed as alpha and beta. So meaning that after you do the estimation, so given the data and you do the estimation, and then you write into the VECM form, and this matrix, this coefficient matrix, tells you everything about co-integration. If this is not a full rank matrices, then you can decompose it into a product of alpha and beta, and alpha and beta defines the co-integrating relationship for the time series, as we see here. Okay, alpha, beta, beta pi, the transpose. So the pi matrix is everything to co-integration. Okay, everybody see that? So again, the Johansen theory is based on this one particular observation. So it's about manipulating or computing for the pi matrices. Okay. So after we do the estimation, we get a coefficient matrix, you get a pi matrices. The first thing we do is like we need to estimate the rank, and usually theoretically, okay, only in theory, the rank of a matrices equals to the number of eigenvalues, or the number of non-zero eigenvalues. Now this definition is only good in theory, okay? Because in practice, you almost never get exactly zero eigenvalues, okay? Because in numerical methods, you have like rounding errors or other stuff, okay? You will get very tiny eigenvalues, like you may get tiny eigenvalues like 0.0001. But the question is that, is that zero or not? Okay, is that zero or not? Do we consider this as do we consider this as a zero eigenvalues, or do we consider this not a non-zero eigenvalues? Now this is very important because ultimately we want to determine the number of non-zero eigenvalues, right? And that in turn determines the rank of pi. So we in general do not know how small is zero. Okay, in general we do not know. So what we do is that we compute what we call a trace statistics for the eigenvalues. Okay, so we order the eigenvalues. Okay, so this is the biggest eigenvalues, lambda 1, and then the smallest eigenvalues, lambda n, and then for each one we compute the log of 1 minus. We compute the log of 1 minus lambda. The idea is that if you remember the log function, what does the log function looks like? Basically, is the log function is 0 at 1. When it gets to 0, when it gets closer to 0, it will go to minus infinity very quickly, right? Remember the log function? I'll show you. Okay. The log function. Oh, what's it doing? Okay, so you see this is a log function. Now the key is that log 1 equals 0. But the key is that when it approaches 0, it goes to minus infinity very quickly. Okay. So we use this. So when it approaches 0, the function goes to minus infinity very quickly. Now we use this observation and do this. We use this observation and check whether something is 0. So basically, when lambda is very close to 0, then this log function is 0, right? Because log 1 is 0. But when it deviates from, when this thing deviates from 0, then this thing will become very negative. It approaches infinity very quickly. So what we do is that we sum up all these values and we get statistics. The more negative it is, the bigger the rank. So here is the procedure to do it. So basically, we start with when equal to 0, and then we check whether we can reject the null hypothesis. If not, then we loop. We check whether r equal to 1, and then we check r equal to 2 until we are able to reject the null hypothesis. Then we find the rank. Okay, so we start with r equal to 0, and then r equal to 1, r equal to 2 until we are able to reject the null hypothesis. Then we find the rank. Okay, so basically it's a way of like checking non-zero eigenvalues, which is the same as the rank of a matrices. Okay. Okay, so after we determine the rank, then we can decompose pi into alpha and beta, and alpha and beta determines the co-integrating relationship as we just discussed. So the idea is like, how exactly do we do this decomposition? Okay, now in this simple case, it's very obvious. Oops, sorry. In this very simple VAR model, then given these matrices, we can identify alpha and beta easily. Okay, but in general, things are not like this. Things are not like this. Given the pi matrices, in general, given the pi matrices, we can't just like decompose it into a product like this. Okay, it's not easy in general, or it's not feasible in general. So what we do is like usually beta is computed as a result of a maximum likelihood process. Okay. Now you can take a look at chapter 6 in Johansen's book, and this is the log likelihood function for co-integration, and this equation is like huge. It's like it fills up like half a pages if I remember correctly. So this is a very complicated mathematics function. But in any case, you don't need to know that. All you have to know is that beta is a result of maximizing this log likelihood function. And the way to do it is to use the software. Okay. So so the idea is after you learn all this, that may become unnecessary because typically in practice, what we do is like we feed the data into a software, and then we compute beta using the software. Okay. So this is how we compute beta. So one of the most popular software to compute beta is R. I think the reason why co-integration theory is so popular in pairs trading is because that there's an R function that compute co-integration. Okay, if there's no software that compute it, then nobody would use it. Nobody would use that, right? Again, each non-zero eigenvalue corresponds to a co-integrating vector. So there could be many betas. Beta is not unique. Okay. But for pairs trading, for real pairs trading, there's only one beta. I mean up to the scale, right? Up to the scale constant. But there's only one beta for our pairs. Okay. Okay, so the trading strategy will be like this. Given a space of liquid assets, remember what we talked about is like the distance method. The distance method. So what we had here is like the distance method is like among the millions pairs, we compute the distance and we pick the one with the smallest distance. But there's no guarantee to work because the smallest distance doesn't mean anything. Okay. It just means that they move together, but it doesn't really quantify exactly what it means by moving together, and it doesn't really define the what we can predict. It doesn't feel right. Okay, it's not statistical properties. So all the co-integration is saying like we replace this concept with the stationarity concept. Okay, So we replace the distance concept with the stationarity concept. So we run the co-integration software among all the pairs that we want to consider, and then we pick the one that are stationary, meaning that they pass the ADF test. And then for the strongly mean-rewarding pairs, we can decide trading strategies among them. Okay, so this is how we construct and trade a pairs using co-integration. I'm not saying that it works. Okay, I'm not saying it will make money and all that. I'm just saying this is one of the most popular way to look at pairs trading from the perspective of statistics, namely using the concept of stationarity. There are many problems with using the co-integration theories for trading in practice. Okay. The biggest problem is that stationarity is a very big concept. It's a very stringent. It's a very restrictive concept. Stationarity is very restrictive. Very hard to be satisfied. Okay. Meaning that like we're gonna do an experiment tomorrow. We're gonna call up the co-integration. We're gonna use it in writing strategies tomorrow. But in general, the problem with co-integration is that it's very restrictive. So let's say as of today, as of today, the data in the we have a 2-month rolling windows, so we have like 40 trading days, and among these 40 trading days, today we can compute the co-integrating beta. Okay, so we start trading using whatever strategy that we want to use. So we get into the market, but then tomorrow, these two assets X and Y may become not co-integrated anymore. Okay, so what do you do in this case? Because yesterday you already get into the position based on the beta computed as of yesterday, and today it tells you the time series is no longer co-integrated. Then what do you do? I mean, it's not clear what you do, right? Well, look, notice that I said that it doesn't give you a new beta. If it gives you a new beta, you can still know what to do, right? Because it's still co-integrated. What I'm saying is that yesterday the time series are co-integrated, and today it's no longer co-integrated. Then you're not sure what to do. And this is really one of the biggest problems using co-integration, because co-integration, it could be like it's co-integrated today. It's co-integrated yesterday, and it's not co-integrated today. And then tomorrow it's not co-integrated again. So this co-integrating relationship may not be persistent over time. And if you are in a market, then it's not clear that what you do on those days that the time series becomes not co-integrated, meaning that they don't pass the ADF test and whatnot. Okay. So that's the biggest problem in using co-integration to do trading. Another problem with co-integration is that it always creates a dense basket, meaning that let's say you have a basket of 10 assets, okay, and then you run the co-integration software on these 10 assets. You will have a beta. You will have a beta that have like 10 non-zero values, meaning that you have to trade all these 10 assets together. Now this is a huge problem, right? In terms of execution. Number one, you trade 10 different assets. It will incur a huge transaction cost. So even though you make money, you may just give all the money to the slippage, to the transaction. Okay. So it doesn't help you make money in this case. Another problem with trading 10 assets is that as the liquidity problem. Remember that when we are saying we want to trade Z, that is a linear combination of 10 assets, we need to trade these 10 assets at exactly the same time, at exactly the price specified. Okay, so and executing a basket of 10 instruments is not a trivial task, if at all possible. It may not even be possible. Okay, if some stocks are illiquid, then you may not be able to buy or sell all 10 of them at the same time. So it create huge execution problem if you use the co-integration that creates a dense basket. Okay, a basket of 10 assets in practice may not be tradable. at the same time. But co-integration requires that all these 10 assets are traded at the same time stamp. Okay. Another problem is that, like, if you have a dense basket, let's say you have a basket of 10 assets, then the structural relationship among them may not be significant enough for you to see. Okay. The third problem with co-integration is that even though you find an optimal mean reverting portfolio that are stationary uh, by co-integration standard, it might not help because the perfectly optimal mean reverting portfolio may just behave like noise, okay? And the variation is so small that it's within a bid-ask spread. Then in that case, you won't make any money of it. It doesn't represent a meaningful step up trading opportunities. Okay. Um, so again, in summary, there are many problems with co-integration. I don't know anybody can make money just using co-integration. Okay. But co-integration gives you a very good concept, or alternatively, it gives you a very good starting point to think about pairs trading. Okay. And then we're going to use that too, but we are not going to use it in this naive form. We're going to use it in a smart way. Okay. So this closes our discussion on co-integration. Does anyone have any question? Anyone got any questions so far? Okay. So let's take a break, like say 5 to 10 minutes, and then we come back with the second half of the lecture. Is that okay? So let's take a break now. Come back in 5 to 10 minutes. Okay. Thank you. Let's get something to drink. back. Um, so so is everybody ready for the second half of the lecture? Okay. So we talk about one problem with co-integration is that the time series themselves could be co-integrated yesterday, and it's not co-integrated today, and it may be or may not be co-integrated tomorrow. So what do we do in terms of trading? I think the fundamental problem with this is that stationarity is a very restrictive requirement on the asset. So one thing we can do is that we forget about stationarity. So what we can do is this. Okay. So let's say today I run the co-integration test and I construct an initial pair using a whatever beta that I compute today. Okay. So today I can create this linear combination of assets. Okay. So this is the beta we compute today as of today. And then we're going to use it. And then we're going to use it to trade for say for the next 60 days. Let's say two months. So we beta from time to time. Let's say 2 months. But then during these 2 months, regardless of what happened, we also use the same beta. But then is how do we describe this mean reverting process? Like what we can do is like we assume a particular beta, we compute a z. Okay, maybe let me try again. Like every 2 months, okay, every 2 months, we compute beta. Okay, every 2 months we compute beta. But during these 2 months, sometimes the time series is not co-integrated, sometimes it's co-integrated, and sometimes it's co-integrated but with a different beta. And we forgot about this. Like what we do is like for these 2 months worth of data, we fit the OU process, the Uhlenbeck process. So basically we compute Z, and then we fit Z into the OU process. Now the thing is like this thing is always possible. Okay, you can always, given any data, you can always fit it into the OU process because this is just parameter calibration. Now, even though the entire process is not mean reverting at all, you can still fit this process, except that you're feeding it very poorly. But you can still fit it, right? I mean, you can always assign some number to this process based on the data. So this is always possible. So in this case, we can just forget about co-integration when we're doing trading. We only use co-integration to find the initial beta. So we need to start somewhere, right? We can't just put in a random linear combination of asset. So we put in a reasonable linear combination of asset. And what I mean by reasonable linear combination is that it's computed, the initial construction is computed using construction. So we get a beta. But after we get beta, then we can look back and compute the time series, stat t, the synthetic assets, and then we fit this synthetic asset into the OU process, and then we trade as if ZT behaves according to this OU process. Now this is always possible because this is just feeding, this is just parameter estimation. Even though the process is not OU at all, you can still fit it. You just fit something very bad. You just fit some bad number. It just fit very poorly, but you can always do it. Okay, and then we decide our trading strategy around the OU process. So this is one way to get around this co-integrated today, not co-integrated tomorrow problem. So we use co-integration only as a starting point, but then and then we trade the asset, the synthetic asset that we created from co-integration, as if it behaves like OU process. Okay. Usually when we have a stochastic process at hand, we want to study the properties of it. So one thing that we can study is the long-term mean and the variance of the stochastic process. So what we can do is that we can write the OU process in the discretized form. Okay. By the way, I changed the symbol a little bit here. So before in the co-integration lecture, I used ZT as the synthetic asset. But after the creation, then the synthetic asset prices will behave just like any other prices. So I changed the symbol to X. So X in this case stands for the prices of the synthetic assets. Okay. So basically, this dCt here is the same as the dxt here, except that this dxt is now in discretized form. Okay. So this is dxt, the changes in X. And then so this tau here is dt. Okay. So this a here is the theta mu. Okay. This minus theta z is minus beta xk. So basically b is the theta here. And then this d wt is just this dt multiplied by the random process, the white noise. So basically, this is the OU process in discretized form, and I changed some symbols. Okay, because I just copy and paste this from papers. Sorry. Okay, and then you can do some algebra, and you can write in this form. So basically, you can see that b is the theta. Okay, and then the long-term mean here, the mu, the long-term mean here in this case is a over b. And then what's B? B is the rate of mean reversion. Okay, so basically after you fit the OU process, you want to ask yourself how mean reverting this process is. Okay, and one way to measure how mean reverting the process is B. Okay, the rate of mean reversion. Now presumably, intuitively, we haven't proved this yet, but we will prove it in the next theory lecture. Intuitively, the bigger B is, the more money that we are expected to make, right? Because we have the bigger B is, we have a stronger mean reverting process, and then we are more confident on our bet, and we are supposed to we are expected to make more money of this kind of process. Okay, so that should be a relationship between B and the expected P&L. By the way, this is the high school mathematics. Basically, you sum up a power series and you can compute. This is the result. Okay, and we're going to use this result multiple times when we do our analysis. So I state so I just state this theorem here. Okay, so let's compute the long-term mean or the conditional means of the price process. So in this second half of the lecture, we are going to distinguish between conditional mean and unconditional mean. Okay, we are going to basically, ultimately, what we want to do is to distinguish these two concepts. So the unconditional mean is like, just given the process, I want to it's sort of like my long-term equilibrium, the long-term returns. Okay, it's not the value that we expect for tomorrow, but it's the value we expect for when time goes to infinity. Okay, so this might not be very useful for trading purpose, because for trading purpose we want to know the value tomorrow, right? We want to make a trade now, so we want to make money tomorrow, right? We don't care about the value in, say, 100 years. Okay. So ultimately, what we really want to compute is the conditional mean. Okay. But in terms of studying the properties of a stochastic process, we just go through the formalities. Okay. So the expectation of xt or xk is just we just plug it into this formula here. Basically, you put expectation on both sides, and then you move this term over here. So this is what we got. So this is copy and paste from the definition. So we group the terms. So we move. This is 1 minus b. So tau. So 1 minus b tau for the mu k minus 1 term. Okay. So this is a tau. We write here. And again, so we repeat the same thing. So we have a definition, right? Mu k equal to this. So mu k can be written in terms of the lag value of mu. And likewise, mu k minus 1 can be written in terms of mu k minus 2. Okay? And again, doing some algebra, we group the terms. And then, so mu k minus 2 can be written in terms of mu k minus 3, which can be in turn written in terms of mu k minus 4 and blah blah up to mu 0. Okay, mu 0 is a given number, a given constant. Okay, and then you do some algebra, and then you see this is the power series here. And we just state the result of the sum of the power series is this. So we plug it in here. This is what we got, and then doing some long-term mean. So this is the expectation of the xk. This is what we got. Okay. So when k goes to infinity, this time goes to 0, this time goes to 0. This is what we got, and this is exactly what we expected. The long-term mean a over b, and then we can actually tell just from this equation here. So a over b is a long-term mean, but we prove it from another perspective. Okay, and likewise we do the same for the variance. We can do the same for the variance. Variance definition. Okay, sigma square. Okay, this a little bit explanation. So basically, you are putting the variance operator on here. Okay. So variance of xk. So we look at the definition xk. So it's the same as the variance of xk minus 1 plus so you need to group the xk minus 1. So it's the variance of xk minus 1 plus the variance of this. Okay, and the variance of this is just like sigma square tau. So you have here sigma square tau, and this is by grouping the variance. Okay. By the way, you have the constant here. The constant disappears because the variance of the constants are 0. Okay, so this is what we got, and again we use the recursive relationship to write sigma k minus 1 in terms of sigma k minus 2, and which can be in turn written in terms of sigma k minus 3 up to sigma 0. And again we have the power series here, the summation of the power series, and using the result, this is what we got. And then we study behavior when k goes to the infinity, which is actually this term here. So this is the long-term variance. Okay, this is the unconditional variance. So basically, given the OU process like this, we know the unconditional mean and the unconditional variance, the long-term variance. Okay. But again, what we really want to do is like these two information, the mean is computed using no information at all from the observations. So this is not what we want. What we want is like, can we use the observation to improve our estimation? So basically, here's what we got. So we just compute this, but again, this is not using any information that we observe. This is just a after fitting, after the estimation of parameters. We compute this. So let's say we want to check Google. Okay. So given the Google data, we do the estimation, and then we can compute the long-term mean. Okay. But this is not what we want, right? This is not good enough because this is the long-term mean. What we really want to do is that I want to know the expectation of k given all the prices from Google. This is what we want. So you need to understand this symbol very well. This is computing the expectation of, say, tomorrow's price, not using any information at all. Okay, this is computing the expectation of tomorrow's price using all the previous prices. Okay, so presumably these two numbers, these two expectations are different, and we want to use this for trading because this is the best estimation of the prices, because it takes into consideration of all the informations available. Okay. So So the rest of this lecture is about how we can compute these quantities. But we need to state this we need to state the problem in a more well-defined mathematical sense first. And so this is the OE process. Basically, again, we do the groupings. We group the xk mass one term, and what we got here. So basically, we have three terms. One in terms of tau. This is just a constant. Okay, this is just a constant, and this is the term in terms of xk mass one. The coefficient itself is also a constant, and then this is the random. This is the white noise. Okay, so this is what make this process is a random process. It's this epsilon k here, the IID white noise. Okay, and again, sigma root tau is a constant. So basically, for this, so given any data like the Google data, we want to estimate it. We want to fit it to the OU process. We need to fit three parameters A, B, and C. We need to fit three parameters A, B, and C. Now what this describes is the true process for the prices. Okay, the hidden state process, the true state of the prices. So xk is the true state. This is something that we never observe. So the true price is not something that we observe. In this model, we distinguished between the observation price, the observed price, versus the true price. Okay, or the true price versus observed price. So the true price is denoted as xk versus the observed price. So what we are saying is that the true price is never observed. So the true price of Google you never know. Whether you are reading from the newspaper, the observed price is contaminated. So basically, can be modeled as a combination of the true price and a noise. Okay, and a noise. So basically, what we have is this. What we have is this. So let's say we have the price for Google. It keep going up, going up, going up, going up. So this is the true price of Google. But this is not something that we actually observe. This is not something that we read from newspaper. What we read from newspaper is this. Okay, we only read when we read from newspaper, we only observe the contaminated price. So it will be somewhere around the true price, but it's not exactly in the true price. You see what I'm saying? So what we observe are these X. These are our observed price. They are not the true price. They will be around the true price, but they are not exactly the same as it. So in our modeling, we model it as so in our modeling, we model the observed price as a linear combination of the true price plus a noise. Okay. So since we never observe the true price, the true price to us is just a random variable. So what we really want to do is not to compute the unconditional mean of the true price. What we really want to compute is the expectation of the true price given all the information. So this can be written in terms of this. So basically, in my symbol, I have yk here. Yk stands for the observation of all the historical prices. Okay, and we really want to compute this. And again, the rest of the lecture is about computing this. But in order for this to be practical in trading, we need to estimate A, B, and C. So basically, given the Google data, we need to estimate A, B, and C. Okay. We need to estimate A, B, and C. Actually, D2. We need to estimate A, B, C, and D. So there are four parameters to this mathematical modeling of the true prices versus the observed prices. And they can be and this A, B, C, D can be estimated from the data. Okay. the way to do it is by maximum likelihood. The typical way to do it is by maximum likelihood. So basically, what it means is that you write down the likelihood equation that involve the parameters, and then you choose a set of parameters that will give you the biggest likelihood of making observations. Let me try to explain this. Anyone play D&D? Anyone play D&D? Anyone heard of it even? See, the old people heard of it. The young people does not know about. The young people don't know about. Okay, D&D is a board game. It's a dice game. Well, it's not a dice game, but it involves luck. So it has dices, and the dices are very beautiful. Let me show you some of the dices. See, you see, these are the dices for D&D. You have a 4 faces die. So the typical dice we have is this. You have 6 faces. Okay, so it generates a random number from 1 to 6. Okay, this is 1 to 6. But for D&D, you have like a 4 face dices. This is very beautiful. It's not like a triangle. But it generates a number only from 1 to 4 because it has 4 faces. And then you have a 8 face die, and it generates a number from 1 to 8. And this is the 10 face dice. Okay, 10 face dice. And this is the 12 face dice. It generates a number from 1 to 12. Okay, and this is the 20 face dice. So these things are very beautiful, right? Because it has so I forgot the word for it. It's not polygon. What do you call it? But this thing is that it has many faces. 1 to 20. Okay. So the idea is that there are many dices. So these dices are not just generating from 1 to 6 like the typical dices. It generates from like 1d4, 1d8, 1d10, 1d12, 1d20. Okay. So let me ask you this interview question. Okay, it's an interview question. Now suppose I'm rolling one dice. Okay, but I don't tell you which one. Yeah, thanks Kevin for the word. Very good. Very difficult word. Yeah. Let's play a game. Let's say I pick a dice from one of those dices like 1d4, 1d8, 1d20, blah blah. But I don't tell you which one I pick. But then I tell you but then I make some I did some rolling, and here are the observations. Okay, so the first one I get 1, and I get 4, and I get 6, and then I get 7, and then I get 8. Okay, and then do I have 1d10 or 1d12? Okay, and then I get 11. Okay, so can you like say based on the observation, can you tell me which dice are used to make the rolls? So what are the options that we get? Like we get 1d4, okay, 1d6. 1d6 are the typical dice that we everybody knows, and then we get 1d8, and then we get 1d10, 1d12, and then 1d20. Okay, so these are the options. So basically these are the possible models that we got. Okay, so I pick one, and then I make some rolls. So these are the observations. So can you guess which dice I used to make the rolls? You can immediately rule out some of the possibilities, right? You can rule out all these possibilities. Now 1d6 can only make rolls from 1 to 6. So 1d6 cannot get 11. Okay. Let's start from the beginning. Okay. So based on observation, you can rule out these four models. These four choices are not possible, right? Because none of them can generate observation 11. Okay. So in other words, we'll say the likelihood for models 1d4, 1d6 to 1d10 are all 0. Okay, it's not possible because they don't generate the observations. Okay, so the two other candidates are 1d12, 1d20. Okay, so which one do we choose? Which one do we choose? The correct answer is 1d12. But there are two ways to come up with an answer. One way is that you can do you can do some quite lengthy computation using the Bayes theorems to figure out exactly the probability of making this observation. So basically we want to do this, right? Given 1d12, what's the probability of making this observation? Versus given 1d20, what's the probability of making the observations? So this P1, this P2, and we know that, like, if you do the math, you will know that P1 is bigger than P2. But without doing the math, you can also see that too. Why? Because from the observation, there's nothing that's bigger than 12. Okay, there's nothing bigger than 12. If you are really rolling with 1d20, then there should be some number between say 19, 18, 16, right, or 15. And since you don't see that, and the biggest number you see is 11, so the probability of making this observation using the 1d12 dice is bigger. Okay, so based on that, we pick 1d12 to be the model. So what exactly? So this is the spirit behind maximum likelihood principles. So what exactly are we doing? It's basically saying among all the possible models that we choose. So among all the possible model we choose. So here I use the theta. We choose one that is most likely to generate the observations. So this is exactly what we have here. So given the model, so in terms of mathematics, it's the probability of observation given the model. So you so in terms of symbol, it's just this P y given theta. So this is what we have here. So Py given theta. But we have multiple when we have multiple theta to choose from, so we will wait. So we have this versus this. Blah versus this. So let's say we have n model to choose from, so we compute these n observations probabilities. So we pick the model that will give you the model that's most likely to generate the observations. Just like in the dice cases, we pick the dices that will most likely generate these observations. Okay. By the way, this is an interview question from CSFB. Oh, they don't call it CSFB anymore. Credit Suisse. But like back 10 plus years ago, when they first merged, they call it CSFB. And this was actually one of the interview questions from the bank. Okay, so if you have time, you're welcome to compute exactly what the probability for P1 and P2 are. You can compute it, okay, using Bayes theorem. One thing that I want to point out is that like picking the most likely model is not the same as the correct model, okay? In fact, in this case, in our example, you could be generating this model using 1D20, okay? I mean, it could be so happen that 1D20 is actually the dice that I picked to make these observations, okay? So the correct model in this case is 1D20, but this is not the model that you pick. So this is very important because the most likely model is not the same as the real model. But the thing is that you never really know what the real model is. You never know because the real model is never observed. If you know the real model, what the real model is, then you don't need any computation, right? So this is a very important observation. It could be so happen that you are unlucky. Say, I mean, 1D20 generating this observation is very small. It could so happen that you are unlucky. The correct model turned out to be the least likely model in your computation. It could be possible. But for trading purpose, I mean, the only thing that we can rely on is the most likely model, okay? Because you never know what the true model is. So, in other words, so given this principle, given the maximum likelihood principle, what you can do is that you write down the likelihood function. So basically, it's saying what's the probability. So the likelihood function is just saying the probability of making the observations given a model. Okay, so the likelihood function written in English is just the probability of sealing the observation or making given a model or given a parameter set data. Okay, and then it becomes a very well-defined mathematical problem now. You just maximizing theta with respect to this likelihood function. So this is an unconstrained optimization problem. This is an unconstrained optimization problem, and there are many optimizers that solve this. Okay, so one popular optimizer is called leader meet, and it can be found in any numerical packages such as R or MATLAB. Okay, but the problem, but the problem with this is like this algorithm does not converge well. Okay, it doesn't in practice. I mean, in theory, of course, it will give you the optimal values, but in practice, this algorithm does not converge to a good enough solution. It does not converge to good enough theta. So what people do is like they usually do a two-step approach. They usually do a two-step approach. First of all, they sorry. Okay. So the typical way to estimate theta is using what we call the EM algorithm, the expectation maximization algorithm. Okay. The idea is this. The idea is like this. Given the initial values, given the initial model, this is the step. Let me try to. Okay, so let's restate the problem again. Okay, this is the likelihood function that we want to maximize with respect to theta. So in other words, we want to choose the theta that maximize this function, and this likelihood function is essentially the same as the probability distribution. Okay, it's the same as the probability distribution, and since this is the probability, okay, we can write it as we can introduce a new variable x. So this is the hidden state variable. Whatever it is, it can be anything, and it's the and this unconditional distribution is the sum of the conditional distribution, conditional upon x. But since you're summing up across x, so x disappears, right? It's just this. When you are summing the probability of A given B, and if you're summing it over B, the P disappear, right? So this is the typical way of this is the typical trick in probability. When you want to get rid of some variable in probability, you just sum over that particular variables. So we write this say unconditional probability distribution in terms of the conditional distribution on x, but you sum over it, so they are essentially the same. Now, what is this? This summation of this p y x given data over x is just an expectation, right? Because summation is just expectation. This is the expectation of this with respect to x. So as you can see here, so this is expectation of this function. So this function is essentially the same as this function because they can be used interchangeably, right? L and P are the same function. So this summation of this P function across x is just expectation of P with respect to x. And the expectation of P with respect to x is the same as the expectation of L with respect to x. So in other words, if we want to maximize L with respect to theta, we can maximize this expectation with respect to theta. It's exactly the same thing. Okay? And maximizing this expectation is the same as maximizing this expectation, because maximizing the expectation of L is the same as maximizing the expectation of the log of L. Okay? And we claim that it's a lot easier to do the maximization of this function compared to doing the maximization of the original function. But in order to do the maximization of this function, you need to know the distribution of x, right? You need to know the distribution of x in order to compute the maximization function. Now this, then this is exactly what the EM algorithm is about. EM algorithm. EM algorithm. So again, we show that like in order to maximize L with respect to theta, it's equivalent to maximizing this expectation with respect to theta. But maximizing this is a lot easier by introducing this hidden variable x. But in order to do this, you need to know x. In order to know x, you need to know theta. So basically, what we have is that if we know theta, because theta is are the ABCD in our Uhlenbeck process model, and theta completely determines the model that that we want to choose, right? So if we know theta, we know everything. Okay, everything about the model. And if we know everything about the model, of course we know the distribution of x, because the distribution of x is determined by the model. And if we know the distribution of x, we can compute the expectation, right? Can compute the expectation. And if you can compute the expectation, then we can choose theta, choose a new theta to do maximization. Maximization. Okay, so you sort of can see this iterative process, right? The idea is that we start with theta 0, and then we do a maximization. And then we compute the expectation, and then we can do the maximization to generate a new theta. So this is the EM algorithm. Exactly why this is the EM. So this is an iterative process to do expectation maximization. And during each iteration, we can compute a new theta from the old theta. And the new theta is supposed to be closer to the optimal values than the old theta. So by keep doing this enough, this will converge. So this is the EM algorithm. Okay. But this EM algorithm is just the general ideas, and there are many implementation of it. And in the paper that I quote from Professor Elliott, they provide two implementation of this general ideas. And this idea is supposed to be much better than the leader-mean algorithm because it has a much better convergence properties. Okay, so it will converge to a better theta than just using leader-mean. Than just using leader-mean, the unconditional optimizer. Now, but the thing is that to use the EM algorithm, it requires theta zero. Okay, so where does the theta zero come from? You can enter anything. You can make up any random number to theta zero. This algorithm will still work, but it just will take a very, very long time for the convergence to happen. So usually we want to have a theta zero that is somewhere close to the optimal values, and then we apply the EM algorithms. So how do we get something that's closer to the optimal values? We can use leader-mean. Because we just mentioned that like this unconditional optimizer will get you a theta. It's just that the theta is not very good. It's close to the optimal solution, but it's not very close. Okay, but it's close enough to initialize the EM algorithms. So in general, when we want to estimate the ABCD in our model, so in general, if you want to estimate the ABCD in our mathematical model, we use the two-step procedure for estimation. We first start using, for example, the leader-mean algorithm. This is an unconditional optimizer to compute the initial model. And then we fit the initial model to the EM algorithm to improve the estimation to get an optimal data. And then this data is the ABCD. Okay, this data is the ABCD. So this determines the model. So this is the so this is how we do the estimation. Okay, it's the non-trivial process. So given the data, we use this two-step procedure to estimate ABCD, and only after we get the ABCD, we can compute the conditional expectation of the future prices given all the historical observations. Okay. So this is basically why I said. And again, in the paper, in Professor Elliott's paper, they provide two algorithms to do the EM algorithms. Okay. Does anyone have any question at this stage? So basically, what we discuss is this: we start with a mathematical model of the Uhlenbeck process to model a mean reverting asset, and the mean reverting asset is computed using co-integration theory. Okay, it's computed using co-integration theory. So we have an initial beta, create the asset, fit the Uhlenbeck process. But in order to fit the Uhlenbeck process, we need to compute the ABCD. And the way to compute the ABCD, we use a two-step procedure. We first start with an unconditional optimizer to compute the initial model theta zero, and then we fit the theta zero into the EM algorithm to to get an improved version of the model, to get a one that is closer to the optimal models. And after we get the ABCD, then now we are able to compute the conditional expectation of the future prices given all the historical prices. So this is ultimately the value that we want to compute. So at this stage, we have the ABCD, we have all the models ready. So we have the Uhlenbeck process. As in the last lecture, as in lecture 1, we want to ask the same question. We want to ask the expected P&L, which we don't compute in this lecture, but we can compute in the next lecture. In here, we can compute the expected holding time. Okay. So what's the expected holding time? The expected holding time is just when we enter a trade, we have a disequilibrium. Okay, and we close the trade when the price is brought back down to the equilibrium, meaning that when the price go from some value to 0. Okay, so basically we enter the trade and then we compute the time that it will enter into 0 sometime later. So this is what we call the first passage time. So the idea is this. The idea is this. So we have a mean reverting process. So we have a mean reverting assets. So it go up, we buy. So let's say 0 is here. Okay. So this is our equilibrium. So this is our equilibrium. And here we sell, right? Here we make a sell. Here we make a sell. So we sell at here. So this is the trade that we make. How do we format this thing? Okay, we sell here. So because it deviates from the equilibrium enough, so we enter a short position. So and then we wait until it goes back down to 0, the equilibrium, and then we close our position here. So so we want to compute this time. So this is the time that after we enter the trade, this is time that it will first enter to 0, and this is what we call the first passage time. Okay, it is the first time that the process enters 0 after we get into a long position, and this is our expected holding time. Okay, this is the expected holding time, and we can compute it. Assuming that we model the process, the mean reverting process, as an Uhlenbeck process, then we can model this. So here's what we're going to compute: the first passage time, which is essentially the expected holding time. Okay. So instead of doing it for a general process, we do it for the standard Uhlenbeck process. So this is the standardized Uhlenbeck process, and the first passage time is computed as this. So C is the time that you T is the value when you enter the trade. So for example, in our example, is the peak. So you enter at the peak and then you sell back when the process gets down to 0, and this is the time. Okay. Oh, by the way, this time is the random variable, right? You realize that this time is the random variable because the time that it goes back down to 0 from C, the time that it takes the process to go from C to 0 is the random variables. Okay, it can take like 1 second, it could take like 10 seconds, it could take like forever, or it may never happen, right? So this time itself is a random variable, so it can only be described by a probability distribution, and this this PDF stands for probability density function, and this probability distribution has a peak value at this particular time. In other words, among all the time possible, this T hat is the most likely time that the process will get back down to 0 from C. Okay. Let me repeat this. The first passage time, or the expected holding time of the trade, is the random variable. Okay. in other words, there are many values to take. It could take 1 second, 2 seconds, 3 seconds, 5 seconds, 1 minute, forever. Okay, and among all this possible time, this particular time is the most likely time, meaning that like this among all the time, like you have different probability attached to the time. This is the time that has the biggest probability to happen. Okay, and we call this is the first passage time. Please notice that this is not the expectation. Okay, this is not the expectation. This is not of the distribution. This is just the value that this probability distribution has the maximum value at. Okay, this is the time that with the biggest probability that it will happen. But this is not expectation of the first passage time. Okay. It's probably possible to compute expectation of the first passage time, but I just didn't find it anywhere in the reference. Okay. And notice that this is not the expectation. So based on everything that we just discussed, then we can come up with a trading strategies. Okay, a simple trading strategy or a sample trading strategies. So what we do is like we given from the Google data. So let's say we want to trade Google versus Apple. Okay. So what we do is that we use co-integration to find a beta. Okay. And then we create a synthetic asset. X equal to Google minus beta times Apple. Okay. And then we fit the synthetic asset into an OU process using the estimation algorithm we just discussed. So using EM algorithm. Okay. To compute the set of parameters required, A, B, C, and D. Okay. And then after that, we can compute the first passage time. We can compute the first passage time. Can compute the first passage time, which is our holding time of a trade position or of an open position. And then we monitor the market. So basically, when the price of X fall below the threshold, fall below a value, we buy. And then we wait. So let's denote the first passage time as T. And then we wait for T period of time. And then we close our position. So, and likewise, when the price is above a threshold, and then we sell, and then we unwind the position after time T. Okay. So this is the sample. This is a sample strategy based on everything that we just discussed today. You see, like all the mathematics tied together. All the mathematics tied together. From co-integration, from OU process, from using EM algorithm to do parameter calibration, they all fit together in this picture. Okay. So we haven't got to the point that we want to compute the conditional expectation of X. So we haven't got to the point that we compute this. But since we are running out of time now, we'll continue this in the next lecture. Okay. So the next lecture is tomorrow, again at the same time, 8 a.m. Hong Kong time or 8 p.m. New York time. But before we leave, does anyone have any question to ask? Anyone got a question? Hector, do you have any question? Or Ken, do you have any question? Okay, so if no one have any question, so I will see you tomorrow. And again, tomorrow is the lab session. please make sure that you're able to run algo quant. Because we are going to do some programming. Okay. So see you tomorrow, and everyone have a good day. Goodbye.